Charles Coulomb was born in 1736. He came from an upper-class family, so he was well educated. He attended college where he studied philosophy, math, astronomy, botany, and chemistry. After graduating, he attended the Royal Engineering School where engineers were trained for military service. Upon graduating, Coulomb served overseas for 20 years, mainly in areas of engineering structures. In 1781, Coulomb returned to Paris to a permanent post where he was no longer working on engineering projects and turned his interest to physics. One of the things that Coulomb turned his attention to was forces between charged objects. Being an engineer, he was able to build some sensitive balances to measure these forces. Here is one of the torsion balances that Coulomb built. Inside this glass tube is a long metal rod. Attached to this metal rod is an insulator with a metal sphere on the end. There is a second metal sphere that can be moved around relative to the metal sphere attached to the rod. Here is an illustration of the torsion balance that makes it a little bit clearer. Here's your metal rod. Here is the conducting sphere attached to the metal rod, and here is the second metal sphere. If you were to charge these two metal spheres, they would repel each other. Sphere E is rigidly held in place so it can't move, so sphere I will move, and that would twist this metal rod. Coulomb had his balance calibrated so that the amount the rod was twisted would tell him how much force sphere I was experiencing. Coulomb could vary the separation between sphere E and I by moving sphere E. So for those different separations, he would determine the corresponding force on sphere I. When Coulomb plotted his measured forces versus 1 over r squared, he saw he got a straight line relationship. So Coulomb found that the force was inversely proportional to the separation squared between the two spheres. The next step was to determine how the force was dependent on the charge on a sphere. Here is a view looking down from the top of the torsion balance. Here is the metal rod. This is the insulator that has the conducting sphere on the end of it. So Coulomb charged this sphere, and let's call the charge on it Q sub 2. He then placed a charge on the second sphere, and let's call that charge Q sub 1. He then brought in the sphere with charge Q1, which repelled the charge with Q2, so the torsion balance rotated, and the amount of rotation told him how much force Q sub 2 was experiencing. And let's say at this point the separation between Q1 and Q2 was 5 centimeters. Coulomb now wanted to change the charge Q sub 1 by a known amount and adjust to a separation of 5 centimeters again and see what the force had become. The way he did that was to take a second identical sphere that had no charge. He then brought the two spheres together, and the charge would redistribute uniformly across them. Upon separating the two spheres, he had a charge of Q1 over 2 on each of them. So we remove this sphere and half the charge on it and bring it back in. And then this charge is moved until the separation between the sphere with charge Q1 over 2 and the sphere with charge Q2 is 5 centimeters. So that will happen when this sphere has rotated back to the left some. The angle of rotation is less, indicating a smaller force, and Coulomb saw that that smaller force was half the original force. So by halving the charge on this sphere at the same separation, he obtained half the force. So the force is proportional to the charge on sphere 1. You would get an identical result if you change the charge on sphere 2, so the force is also proportional to the charge on the second sphere, q sub 2. And we already saw that the force was inversely proportional to the distance squared. With this balance, Coulomb found that the force was proportional to q1 times q2 over r squared. Introducing a proportionality constant, we have Coulomb's law. And this is how Coulomb's law was written for over 100 years. When Oliver Heaviside was consolidating the equations of electromagnetics, he rewrote this k as 1 over 4 pi epsilon sub 0. By incorporating a 4 pi here, he removed 4 pi's from future equations. We will shortly see why incorporating a 4 pi here will remove 4 pi's from future equations. It essentially comes from the fact that the surface area of a sphere is 4 pi r squared. This constant epsilon sub 0 is called the permittivity of free space. The value of epsilon sub 0 is 8.854 times 10 to the minus 12th farads per meter. The value of 10 to the minus 9 over 36 pi is very close to this value of the permittivity of free space, so we will often use this form for epsilon sub 0 because we can set up problems that we can solve without using a calculator that way. Force is a vector, and the direction of the Coulombic force is along the line between the two charges. Here is where the concept of position vectors are going to be useful. So if Q1 and Q2 are the same sign, the direction of the force will be the direction of this vector r that points from Q1 to Q2. And that will just be the position vector of Q2, r sub 2, minus the position vector of Q1, r sub 1. The unit vector pointing from Q1 to Q2 is just the vector r divided by the magnitude of the vector r. So we can use this unit vector to incorporate the direction into Coulomb's law. If the charges are of different sign, that will introduce a minus sign and change the direction of the force from repulsive to attractive. We can replace the magnitude of r with the magnitude of r2 minus r1, and this unit vector with r2 minus r1 over the magnitude of r2 minus r1, and have an alternative expression for the Coulombic force between two charges. Let's look at the situation when we have multiple charges. Let's start with 3 charges. We're going to find the charge on Q due to 2 other charges. Let me first bring in Q1, and Q will experience a force due to Q1, and let me call that force F sub 1 and represent it by this arrow. Let's next remove Q sub 1, and now let's bring in Q sub 2. So Q2 will cause a force on Q, which I will label F sub 2 and represent by this arrow. Now let's bring back Q sub 1. What you would find is that the force that Q experiences in the presence of both Q1 and Q2 is the vector sum of F sub 1 and F sub 2. This is an important concept that superposition holds with Coulomb's law. Let's look at the Coulombic force that Q experiences from n other charges, which are labeled Q1, Q2 up through Qn, and they're at position vectors R1, R2 up through R sub n. Let's first determine the force on Q due to an arbitrary charge Q sub k. We will use this expression for the force between two charges that we developed earlier. The vector that points from Q sub k to Q is R minus RK. Here is our expression for the force on Q due to the charge Q sub k. We will have a similar expression for the force on Q due to each charge, and since superposition holds, we can just sum all those. So it will be the sum from K equals 1 to N.